Reminding you that Monday, October 8th, is the mid-semester examination. So we will do that Monday in this class. Okay. Time flies when you're having fun. Okay. Good. So this test that I've handed out is representative of the type of questions you might see on midterm. I failed to do this in the last class. It's very representative of what you might see on midterm. Good. So first question, so this is just looking stuff up, right? What is an operating system? Remember? Does anybody remember?
It's an abstract.
It's an abstraction layer that gives you access to resources. And what's the second thing that it did? Not only did it
manage the resources,
it manages those resources. So it's both, they're both associated with the resources. It's an abstraction layer, okay, that gives you access to the resources. And then under the covers, it manages those resources. All right? That's what an operating system does. So if someone asks you what an operating system is, you now know a really good answer. All right? All right, excellent. And this is just that, I think we've done over this one several times in class. You just kind of fill this out. You know,
Oh, yeah.
if you want to give me some justification for it, what you put, I'm happy with that too. Okay, I'm not saying that any answer is good, but if you give me something, if what you put down and what I think is the right answer differ, and I don't see any rationale behind your reasoning, then I'm going to mark it wrong. Okay? So if you're not sure, you can give me rationale. All right?
so for whatever answer we have here, we also have to give you a reason for it?
If you think that I'm going to differ in that perspective, for example, if you say to me, I think that the operating system, in class we kind of agreed that that's primitive, right?
Mm-hmm.
You know, but if you say, well, no, that's modern, and here's why, I can be convinced, right? So, I mean,
We can say it's experimental.
right? So,
Debate it.
so again, you have to give a justification. And remember, my view on it was, as far as is it production or is it experimental, was what was it used for?
Okay.
Experiments.
No, it wasn't. It was used to do production work.
Yeah.
It was the Dijkstra's machine was so they had something to do their work at the college.
Yep.
You know, word processing and run codes. They weren't doing computer science research. Okay, as opposed to, say, the nucleus, where that was clearly an experimental, they were doing research, right? So it was an experimental kind of a scenario. All right, good.
What about that? That's on the last one is Unix. I'm sorry.
Yeah, well, that should be pretty obvious.
Modern,
Yeah, modern.
extensible.
Well, we could argue about that.
Yeah.
So, I mean, the argument there is it's open source, so I could glue additional stuff on there. You know, I personally look at it as a fixed operating system. In what way did you extend Ubuntu when you put it on that machine?
Well, we didn't actually.
You didn't. You just installed it.
Right.
Boom, as a production
But can't.
operating system.
So when part of that on there is a part where you said you can add devices and
You
stuff.
can.
So wouldn't that
can
be
do
extensible?
So if you want to say that it's extensible, then you ought to put something like that as a justification, right?
Mm-hmm.
So if you're not if you're not sure how I'm going to flip the coin, then the safest thing is for you to put down why you think it's true, right? But then again, there's what, 10? How many questions? However many questions, you know, if you want to waste a bunch of time on, now, you know, it's 15 point or so, assuming that this question even shows up. I mean, you know, it may not even be here.
Mm-hmm.
Okay, but can I ask one more? I got to debate you on one more thing about it. When he says experimental or Production. Isn't that kind of like both?
So what I'm asking is, what's the purpose of the machine and the operating system?
Well, you can. It is experimental because you can do, you know.
Okay, so this is the argument I get into with my boss at work. He says, oh, we do research with computers at work. And I'm going, no, you don't. Yes, we do. We've got this big supercomputer. That's all we use it for is research. And I'm like, no. Okay, what, so it would be like if I'm an oceanographer doing research on oceanography, and I drive a car to work and back.
Is the car part of the research?
The car isn't part of my research.
It's just a tool.
Simply a tool that I use to get to work and back.
That's not fair.
And so it's not associated with oceanographic research, and neither are the computers at my work associated with computer engineering research. They are simply a production system. Okay, they don't want us dorking around. Let's try this and let's try that, and let's change the block size here, and let's add this driver there.
But the fact that it's open source, doesn't that kind of, you know, say that it does?
You could argue that, but again, if you want to argue that, then
Because that ain't right. Okay.
write it down.
Dr. Morris.
So I view it as production. Yes.
Dr. Morris, could you give us an example of what you think is a real experimental system?
Sure. So the Hydra system, right? It was clearly experimental because what were they doing with it? They were doing experiments on operating systems, how to do research in operating systems, right? As opposed to Unix, which is pretty clearly a production system. Now, is Unix used to do computer science and computer engineering research? Absolutely. I grab the open source Linux kernel and I do some, you know, I tweak it, I play with the file system, okay? But, you know, at its core, the purpose of it is to give people a production operating system. Like, what's Windows? Windows is a production operating system.
Yes.
You install it on your machine, you do whatever it is that you're doing on that operating system. Could you dork around and do some experiments? I'm sure Microsoft does it all the time, right, in their back room. They got a bunch of, you know, guys, you slide a pizza under the door every 2 or 3 days. And they're
Wow, this is fun.
So the next question is just, do you understand what a process is? Okay, so if that question shows up, you should know something about what processes are. And the opening set of slides that I gave, Lecture 1, has a lot of this kind of information in it. Your undergraduate textbook, you make sure you grasp the notion of process. And again, out of the first slides that we looked at, we talked about in a multi-programming environment, remember the states that a process can be in, right? Mm-hmm. And then there was a certain kind of a transition that took place. Right, running, block, ready, and when did it go from each state to the next? So some words about that, okay? Good. We talked about scheduling algorithms. And some of them can lead to starvation, right? And so if this shows up, you should have some idea of which kinds of algorithms might lead to starvation and which won't. And then part B is why. Part C is how do you deal with starvation in general. And then part D is, okay, for the ones that you picked, whatever set you picked in B, tell me what you would do to fix it. All right?
Was priority and
Whatever they are.
shortest job, right?
Okay, so the next one is just, you know, this is actually closer to what V7 is. Okay, Unix V7 file system. We've looked at the one we've looked at. We've only had single indirect. Turns out that V7 ended up having direct, then single indirect, double indirect, and triple indirect blocks in the inode. All right? So I'll do a boil down simple case of that to make sure that concept is clear.
Dr. Morris, what was the difference between direct and indirect? Direct just would.
I'll show that now. All right, so if I have an inode, remember what's in an inode? At the top, what were some of the things that were in an inode?
Here.
All the metadata, the attributes of the file. Permissions, is it a regular or ordinary file? Is it, what's its size? When was it modified last? Timestamps, blah, 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 all that stuff. So we'll just call these the attributes. All right, then what goes down here?
Parent and
A list of addresses.
Okay, yeah.
Now let's suppose that this is set up so you've got D0, D1, and D2. These are direct blocks, okay? The idea there is that the data is directly in those blocks. So suppose that a block could hold, suppose a block holds 8K. All right, so I've got an 8 kilobyte block. All right. Now suppose I had a file that was 24 kilobytes. Then how many blocks would I need?
3.
And there they are. Direct block 0, direct block 1, direct block 2. Right? What if it was bigger than 24K?
You need 4, but you would need not the whole 4.
Then you need single indirect. Okay? And what that does is it points to another 8 kilobyte block, and suppose that a block itself can hold, I don't care, 100 addresses. So, D0 all the way through D99. All right? All right, so this points to, all right, so then, here I've got 1, 2, 3 blocks. And then when I run out of room in the 3 8 kilobyte blocks, I go to a single indirect. There's one level of indirection. Now, so it points to a block that's no longer used as data, right? This is data, right? And now these are the same size, even though they don't look like it. This is no longer used as a data block. It's used as what? A block of addresses. So how many data blocks could it point to?
From 0 to.
So look, data, data, right? So if there's 100 data blocks, now how much can it hold? Well, you've got the 24 from here,
103.
right? So you got the 24, yeah, altogether 103 times 8 kilobytes.
Dr. Morris, I have a question. Now, here in this quiz, we had 3 inodes, right? Now, as long as we have the option of covering all the bytes with the first inode, we don't need to go into the second inode. Is that the point?
You never have more than one inode per file. An inode never has more than a file has exactly one inode. Okay, exactly one inode. Right?
I guess that kind of threw me a little bit too, because it was like you know, I know you said we had spare parts, but it's like we're supposed
I
to.
meant you wouldn't use, because remember, if
Can we go over this?
yes. If I go out to the free list and I say, give me an inode, it's going to give me an inode address, right? But there's going to be plenty that haven't been used. That's what I was trying to illustrate here. So let's finish this and we'll go over the quiz. All right? So now, so altogether here I can have 100 blocks plus 3 blocks. And each block is what?
8 kilobytes.
8K. So 8K times 103, whatever that is. $824 kilobytes, right?
Dr. Morris, I know you said it's 100 in that 8K. You said there's 100 addresses in there, right?
Yes.
So you count the direct data blocks over there 3 is the 103. Is that what you getting your?
This is 8K. This is 8K. This is 8K. The fact that this is 8K is not relevant. What's relevant here is that it holds 100 addresses.
So where do you get the other 3?
And then here's the 8K, 8K, 8K. So you get the 3 from
Okay.
the 3 that are here,
Okay.
namely 1, 2, 3, and then the 100 that are here.
Okay.
All right? So the largest file that this one can hold is what? 820. Well, what if it's bigger than that?
You have to
Then you
add.
have what's called a double indirect. And here's the way that one works. It goes to an indirect block. How many can an indirect block hold?
100?
100. So 0 through 99. And each of these in turn points to another 0 to 99. You see it?
Now, Dr. Morris, we're saying 100 for the matter of simplicity, right? It doesn't have to be 100.
It's whatever number it is. I'm just making up the numbers here. So I said it was 100 arbitrary.
Right.
It depends on the structure of the file system. So in this case, how many, and then each of these in turn does what? Eta,
Block.
right? Eta, right? All the way down. So then, how many data blocks are there now? Each of these is 100, right? Each of these points to 100.
10,000?
And how many of these are
So
there?
that's 10, yeah.
There's 100 of them, right? So there's 100 of these, and each of those has 100. What's that called? 100 squared, isn't it?
10,000.
Right? Times what? Times 8 kilobytes. You see it? So whatever that number is. All right?
8,000.
Okay? So 10 squared times 8. So 8 times 10 to the 4th. Right? It's 8 times 10 to the 4th. If I did my math right. I think I did.
Mhm.
Okay, then plus the 824 you got here, right? So that's how big the file can be now, right? What if that's not big enough? Then I use a triple indirect. Here's how that one works.
I mean, you can go all the way down to it.
Okay? So first of all, I've got a block of 100, right? And each of those points to another block of 100. Right? And then each of these points to a block of 100. Right? And then what?
Then we have the data.
Finally, you get to the data. You see? Triple indirect. 1, 2, 3. So what is that clearly going to be?
So it's 10 raised to the power 3.
It's 100 cubed times 8 kilobytes. You see it? Do you see why? Right? Because this is 100. Okay? You pick one of those, that's another 100. You pick the top one of those, that's another 100. So there's the first 100. Then the second 100. Then the third 100. The 99th 100. The 100th 100. And oh, I go to the second address here. Okay? So let's see. That's 10 squared cubed, which is 10 to the 6th. 8 times 10 to the 6th. So there we go. So 8 times 10 to the 6th. Right?
Couldn't you just say 80 times 100 cubed?
That's what I did. That's what I did. 8 times 100 cubed.
Oh,
All right, so whatever that is, like 8 megabytes now. Right?
Question.
Yes.
Can you say where you left that, the 10 square and cube?
Sure. So look at the diagram that you've got. The numbers are different. The pink represents a triple indirect block. So how many does that pink point to? 100. Right? And so how many of these light blues are there going to be? 100. There's 100 in the pink. And then that means that there's 100 of the blues. And each of those point to 100 of the yellows. And each yellow points to 100 data blocks. Right? You see it? All right. And by the way, this could continue, right? This could continue. All right, so now, the quiz question Maurice had. All right, so can I erase this? So let's get the original structure. What was on the free inode list? Come on. Here's the inode list. This is an operating system structure, and what does it have in it? It's got free inode numbers. And what were the numbers that were on there? Say it again.
21, 73, 49.
Right, and then probably some more, right? And so if I say to you, I need an inode, and is it pretty clear that down in the bowels of the operating system, there's going to be a function that's named something like get free inode?
Yeah.
Right? Get free inode. What do you suppose get free inode is going to do?
Once you go get a free
It's going
inode.
to look in this list, and it's going to pick one using some approach. It's going to return that number to you, and then it's going to take it off the list. Does that make sense? And what does this 21 correspond to?
A free inode.
Yes, somewhere on the hard drive, that number 21 maps to an inode. And we don't really care how that happens. There's some other piece of operating system code at a lower level that does that. So it's hierarchically structured. All right, then, what's another operating system structure that you need? It's called a block list. All right, and what were the free blocks?
84, 71, 16, 94, 20, 86, 11, 17, and 63.
And so on and so forth. Same idea, right? So just as there's a low-level operating system function called get free inode, there's going to be a low-level operating system function called get free block. Right? By the way, let's just speculate if there's a get free inode, you suppose there's a free inode, or free inode. Get inode and free inode. Get block, free block. Right? So what does the get inode do?
They go
It
get
returns the inode number. What do you suppose the free inode does? It takes the number that you send it, puts it back on the list. Right? So allocate, deallocate. Inodes, allocate, deallocate blocks. Now what was the directory? What did it look like? It was an empty directory initially, so it had dot and dot dot. And what was dot?
12,
And what was dot dot?
27.
Not,
Did I have dot dot at the top? Okay. So what was dot dot? And what was dot? 37? What do these correspond to? Inode, yes. This is the inode of the current working directory, and this is the inode of
The previous.
the parent
The
working
parent.
directory. Here, here. Yes. So we should always celebrate our parents. So if I were in this directory, wherever it is, and I did an ls, what would show up? Nothing. Because there's no files. What if I did an ls-l?
Everything would show up.
Then dot and dot would show up. What if I did ls-li?
The inodes would
Then it
show
would
up.
show
No, it's
dot 12,
12.
and it would show dot 37. Okay, but there's no other files in that directory. Now, what were then? We had over here a whole bunch of blocks. So for each of these in the block list, that means that somewhere there's a block. Agreed? So, and what were we asked, what was the file size?
295.
295.
Was 295 bytes. And let's see, what kind of file was it?
It was
data file.
It was either a regular or an
Ordinary.
ordinary file. So we'll just use R for regular. Okay. And what other type of attributes are there? Did it have a name? What was the name of the file? It was called q5.txt. And there's some other things, right? There's the timestamp, there's the permission bits, blah, 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 blah. Okay. Now I'm going to create that file. So what's the first thing I need to create a file?
go get some free inode.
Okay, get inode. So I call the operating system structure, and it goes to the free list and goes, now it doesn't matter which one it picks. So let's say that it picked the 45. Doesn't have to. Okay, so if it picks 45, point, and returns it to caller. Now, inside the caller space, he's got the image of an inode, correct? That corresponds to inode 45. So this corresponds to inode 45. Inode. Yes? So what's going to go in the attributes associated with that inode?
The
File size. And what's the size?
type of file.
It's 295. Type is going to be regular. And remember all that other stuff? Okay. Timestamp, mission bits, da-da-da-da-da. Now, the next question. How many addresses does this inode hold? How many did it say it held?
You had 3.
It holds
No,
3?
it had 4.
I thought it
It
holds up to 4. Okay, up to 4. So this could have an address 0, an address 1, an address 2, an address 3. Correct? Now, how big's our file? 295. How big are blocks?
64.
64. So how many blocks are we going to need?
5.
Uh-oh. Let's see. 1, 2, 3, 4. Uh-oh. Right? I can't fit 5 blocks in 4 addresses. So what am I going to do in this example of a file system?
You're gonna
I use the blocks as indirect blocks. Now, how many addresses does an indirect block hold?
4.
Also up to 4. So I take, what do I need for A0?
1. You only need 1 address.
Oh, only 2? Okay, good. Thank you. Inodes only hold 2 addresses. There.
Oh, yeah, that's
Sounds confused.
All right, only hold 2 addresses. And an indirect holds 4. Okay, so, excellent. Here we go. So what do I need first?
0 through 63.
Don't I need a block to use as an indirect block?
Mm-hmm.
So I go and I say, get block. Right? So I go to the operating system function that gives me block numbers, and it says, here you go. Here's block 63. Now, it doesn't know how I'm going to use that block. I might use the block to put data, or I might use it as an indirect block. The operating system doesn't care. All it says is, no one else can use 63 because this clown has it. So now, what goes here?
63.
63.
0 through 63.
All right, 63. Now, is it pretty clear then I'm gonna need 2 indirect blocks.
Yes.
Because I need a total of 5 blocks, don't I?
Yes.
Right? And so I say, okay, I need another get block.
So you just chose 63.
Yeah, it could have been 84 would have been the correct answer too.
Yes.
Just anything off the free list. Okay? I need another block. And it goes, okay, here you go, 17. So now I've got my 2 indirect blocks. Yes? And what do they look like? They look like this. Here's block 63, and here's block 17. Now, in this case, they are not data blocks. They are what? They're used as indirect blocks. This is block 63, this is block 17, and I've got A0, A1, A2, A3, A0, A1, A2, A3. How many data blocks do I need?
For pi,
And what do I need? 5.
because it only holds 64 bits of memory in each
64 bytes per block,
at 295 blocks.
right? And that corresponds to